Okay, so this is our second lesson from chapter 13. And last time were looking at scalar surface integrals, and now we're going to take it down a dimension and think about what happens if we were integrating, we like to integrate, for example, along a wire and figure out the mass of a wire given the density of the wire at any point. So let's review, we did this in a little bit in Calc 2, but let's review how we would do it just for a straight wire first. So let's suppose this is our straight wire and we're just looking at the part of the wire between A and B. I only need one dimension to describe this wire. So that's the wire in yellow right there. And then suppose that I give you some density. The density is varying, so maybe this wire is lighter over at this side and it's heavier over here. And we'd like to figure out the mass of the wire. So the units of the density I'm going to give you are going to be units mass per unit length. And our steps are going to be really similar to what we've done anytime we're trying to find the value of something that varies over a region. We're going to chop up that region. In this case, we're chopping up the wire into n little pieces of length delta x. So let's just imagine we do some chopping here. And this one would be x1, x2. We'll just call this one down here x sub I. Okay, and then we're going to zero in on one of these pieces. So let's just zero in here on this little piece. And we'd like to approximate the mass of that piece. And so we can do that just like we've been doing this all along with finding mass of our 2D regions. The mass of this ith piece is going to be approximately equal to the density at that point. In this case, now times delta x. Because of my units, you can see that this is times delta x because my units of density were mass per unit length. Okay, so let's put this down below because we're going to need this. And that would give us the density, or excuse me, the mass of just that ith piece. And we're going to add up the mass of all the other pieces. In this case, I only need one sigma because it's only one dimension that I'm adding in here. And then I'm going to take the limit as the number of pieces I chop that up to goes to infinity, which would mean the size of the pieces is going to 0, or the width of the pieces. So limit as delta x goes to 0, which is the same as n going to infinity. And we can see here's a limit of a Riemann sum. We're getting pretty used to this now. The shorthand mathematical notation we have for this is a definite integral, in this case over the region from A to B. And my integrand is just going to become the density dx. So we define this by a limit of a Riemann sum. But rarely do we actually evaluate it by doing this full-on limit. Usually what we'll do is use the fundamental theorem of calculus if it applies, and just evaluate this definite integral like you learned to in Calc 1 and 2. So now let's extend this, because what if my wire was not just a straight wire? What if it was curved? So let's sketch a new example here. And so we're going to start with the same idea. We're still going to chop up the wire. And I can do this still into n pieces, but the length is going to be different now. I can't just call it delta x or delta y, but we have a parameter that we use to help us figure out the length along a given curve. And if you said it was s, you're correct. Remember how we've been using, we'll call this delta s right here. And let's say we wanted to approximate the mass then of just this ith piece right here. So now I have this point, and it has both x and y coordinates. So this is the point x sub I, also y sub I. And I can find, let's put delta s here. So I can approximate the mass of just that little piece by taking the density at that point now times delta s. And notice the units of my density are still units of mass per unit length, because ultimately at the end of the day, I'm going to consider this wire to be what I call a one-dimensional object sitting in two-dimensional space. And the way I'm determining the dimension of an object is how many parameters you would need to describe where you are on the object. I could write this, I could parameterize this curve all in terms of s, or even in terms of t if I wanted to. So I really only need one variable, t or s, to describe where you are at any point on this curve, which is why we're considering this a one-dimensional object. So I'm just doing mass per unit length instead of mass per unit area. I'm considering a one-dimensional object in two-dimensional space, and we'll keep talking about that a lot as we move forward, the dimension of objects. Okay, so now let's start to add this up and take a limit and see what we get. And again, we see this is a limit of a Riemann sum. So in shorthand notation, we can also write this as an integral. In this case, we're going to do it, we're just going to write over the curve C here to let us know that we're going to integrate over this whole curve. And my integrand is going to just become the density ds. And we haven't seen an integral like this before. This is a new type of integral. We've defined this, if you notice, as a limit of a Riemann sum. But I can't evaluate it yet in this form. And the biggest issue is fundamental theorem of calculus won't work here, because right now I've chopped up this interval in terms of s, but I'm given the density in terms of x and y. And I need to get everything in terms of the same variable, just like up here where we had x and we've chopped up in terms of x. So in order to use fundamental theorem of calculus, I'm going to need to change variables with this integral here, and then get everything in terms of one variable. Then I'll be able to evaluate using fundamental theorem. So let's see how we can change variables to get this, rewrite this integral so we can evaluate it. So I want to generalize what we just did. We were defining how we could find the mass of a wire, but in general, the type of integral that we found, where I'm integrating over a curve, some function of two variables ds, or I could even be doing this, it could be a function of three variables, because my curve could be this, like a helix or a wire that's in 3D. The same idea will hold. This is what we call the line or path integral. And I really dislike that name just because it doesn't have to be a line that you're integrating over. So path is probably a little bit more accurate. But that's just you'll hear it called a line integral all the time. Physics notation, just for those of you that are also taking physics, is often you'll see f and then they'll use L, dl instead of s, but we're both talking about the same idea. All right, so how do we evaluate? We're going to need to change variables, and we like to put everything in terms of the same variable. The easiest way we can do this is by parameterizing the curve. And so recall, back from chapter 10, given a curve, we can come up with an associated position vector function that sweeps out a curve that's parameterized by x of t and y of t. And then this means I can rewrite, the goal will be to rewrite my entire integral in terms all of t, because t is an easy thing for me to be able to parameterize in terms of. S is trickier, because as we learned back in chapter 10, you can parameterize a curve in terms of arc length. It just gets hard a lot of times. It's not always an easy thing to do. So it's much easier just to say, all right, it doesn't have to be parameterized in terms of arc length. I can just parameterize in terms of time, or t, this other variable, and then rewrite everything. All right, so once you've parameterized, you're going to use that parameterization to rewrite the integrand, because now everywhere that you have x, it's going to be replaced with x of t from your parameterization, and everywhere you have y, it'll be replaced with y of t from your parameterization. And now we need to rewrite ds. And so again, what we're trying to figure out is how does ds relate to dt? Basically, what's the Jacobian that I'm going to have here? And a nice thing to recall, and we proved this when we were doing arc length back in chapter 10, is that ds dt is actually just going to be your speed of your parameterization, which means that ds can be written as the speed dt. And if you're saying, oh wait, that doesn't make a lot of sense, how did she do this? What I'm really doing in between is I'm saying that ds can be thought of as ds dt, which is the same as speed dt. Okay, and so really this speed is actually your Jacobian. And I know we didn't get it by looking at the determinant of a matrix, but you really could get it from that idea. So think of that as just the Jacobian. All right, so let's rewrite everything. So when I would like to evaluate a scalar line integral, I'm going to change the integrand to be all in terms of my parameterization, x of t, y of t. I'm going to find the Jacobian, which will be the speed dt. And again, why I want us to think about why that would make sense. This is a tiny little distance, and we're saying that distance is my rate times my time, which is something that intuitively we have experience with. We know that if we're driving a car, our distance we've gone is going to be our rate times our time. And this is saying like our tiny little distance will be our instantaneous rate times a tiny little time. Okay, now let's remind ourselves how we find our rate, or the speed. Given this parameterization up here, I'm finding the magnitude of the velocity. So that means I'm taking the square root of the derivatives of the components, squared and then added together here. And this, what's great is this whole idea is going to extend to if we were integrating along a curve in 3D. So now my curve might be like a helix, and I'm still going to be chopping up along the curve in terms of s, and then I'm going to change variables. And I will still have that the Jacobian will still be the speed dt. And in this case, we can just rewrite that as the square root of these terms with the dz dt term added as well. Okay, so let's go ahead and practice this now with a couple of examples.